Okay, in the last class we have seen some salient properties of nonlinear systems. First we saw that the property of the state space is not the same everywhere. There are some part of the state space in which one property pertains, another part of the state space another property. So, that is one very important feature of a nonlinear system, that it is not the same everywhere. We have seen that in the simple pendulum also there was one equilibrium point with circular orbits around it. There is another equilibrium point with saddle character. So, that around these points the behavior would be entirely different. So, if you take any initial condition away from these points, they will be guided by some property of that local region of the state space. So, you have that as the fundamental shift from your knowledge of linear systems. Now, apart from that, we have seen that in some cases it is possible to work out the behavior of the whole state space by working out piecemeal starting from each equilibrium point. So, the standard procedure would be that look at each equilibrium point. In a nonlinear system there can be many equilibrium points, and for each one you work out the local linear neighborhood and the behavior around it, and then from there it is possible to sort of extrapolate the vector fields to the rest of this state space. Now, this procedure also fails under certain conditions, we will see that. But one thing I did in the last class, that was to point out that the exactly imaginary eigenvalues were somewhat unnatural condition, because in that case the real part has to be identically 0, and you pointed out on the day that the particular example that we had taken there, what was the shape of the Jacobian matrix? The Jacobian was, let me see what it was, the x double dot plus x minus x cube, that was the system, right? So, what was the Jacobian? 0 1 minus 1 plus 3x square and 0. Now, because these two terms are 0, so whatever be the x, it will always turn up into complex purely imaginary eigenvalues. But the point is not that. Point is, here what are we doing? We are locating this equilibrium point and then arguing that this would represent the behavior around it. Now, this would represent the behavior around that equilibrium point. Away from the equilibrium point, say another point here, then the same logic will not occur. So, simply by substituting this particular x value here will not give you the proper Jacobian matrix here. So, that is why the right way of working out the real character of the state space would be to start from an equilibrium point, say here, from initial condition, say here, and then work out by Runge-Kutta method. That way you will be able to plot the evolution of it. Now, if that comes back to itself, you know something that it is really complex conjugate, but around it the local linear approximation that yields a purely imaginary eigenvalue is correct. But it can also be like this, then you would infer that no, it was not really correct, very approximately correct, it is correct only at that equilibrium point, elsewhere it becomes somewhat wrong. So, that was the logic. In general, if you have a term plus something x dot plus something, then that term will lead to that real part, and then it could be whatever. That means, in a system like this, you are actually assuming that this part is identically 0, that is why it was yielding purely imaginary eigenvalues. Anyway, so the point is that in some very simple cases, it is possible to work piecemeal by looking at the local linear neighborhoods of each equilibrium point. But under certain condition that has to be taken with a pinch of salt, but there are situations where it cannot be done. And we had analyzed one situation in the last day, that was x double dot minus mu 1 minus x square x dot plus x is equal to 0. This equation we had handled in the last class. We had decided, we had concluded that for mu less than 0, it will be an orbit something like this. For mu less than 0, and for mu greater than 0, it would be locally like this, but that is a local linear approximation which might not work, there is no reason to believe that it will also work elsewhere. So, there it will still be an incoming orbit. So, in between there will be an orbit which is maybe something like this, where if you take an initial condition inside, it will converge onto that. What?
Draw the inner one anti-clockwise. So both are in the same direction.
Both are?
The inner outgoing spiral is clockwise.
No. Was it clockwise or counterclockwise? Check that once. I mean, both have to be in the same direction. It cannot be the inner one is counterclockwise, the outer one is clockwise. That is not possible. Why not possible? Because as you come very close to this, if you take a slight perturbation this way and slight perturbation that way, they cannot lead to opposite vectors. That is why they have to have the same kind of rotation. Fine. So, this is the example of a limit cycle. Now, one very common misconception, let me first clarify, that you have come across situations with such closed orbit. For example, if you have purely imaginary eigenvalues in a linear system, then what do you have? You still have like this. We have seen that, and we have seen. So, this is purely imaginary eigenvalues in a linear system, and second is the limit cycle, which also looks similar. So, is there any difference between them? Can this be called a limit cycle? No. Note the word limit. If you start with a different initial condition in a case with purely imaginary eigenvalues, say you start from here, it will go into another loop, a different loop, not the same loop. Start from another initial condition, it will go like this, a different loop, not the same loop. While in this case, if you start from another initial condition, it will converge onto that. Start from another initial condition, it will converge onto this. This is a fundamental distinction. That means, starting from different initial conditions, this one leads to different orbits, albeit with the same frequency that we have seen already, but here they all converge onto the same orbit. That is why this is not a limit cycle. So, this is not a limit cycle, this is the limit cycle. So, whenever you see a cyclic orbit, do not call it a limit cycle. One of the very common mistakes that students do. This is not a limit cycle, this is a limit cycle. Okay? Because in the limit it reaches this, while in the limit there is nothing that it converges on. So, that is one important property of a limit cycle. Secondly, you would notice that if you have an orbit like this, and if somehow it gets perturbed, then it comes back to this one. While if you have an orbit like this, somehow it perturbed, it goes into another orbit. So, it is in those respects different, and it is not difficult to realize that wherever we need some kind of a oscillatory motion in a physical system or an engineering system, we really have to do this. Why? because there are always some perturbations, there are always something to disturb a particular motion in nature or in engineering systems, and in all systems we would like it to be stable. Whatever we want to be a stable behavior, and you can see that this is a stable behavior. So, where do we need a oscillatory motion in engineering? Any oscillator, all the oscillators that you have heard of, you want that to oscillate with a definite frequency, with a definite amplitude, and that is possible only if you design something like this, not like that. So, none of the oscillators are really linear systems with purely imaginary eigenvalues. All oscillators that you have studied in, say, electronics, they are all harboring limit cycles. Now, with that knowledge, with that concept, you can go back to your books in electronics where you studied about oscillators, the simple oscillators that you probably studied. What are the oscillators you studied then? Huh? Okay, and Colpitts, Hartley, yes. So, all that you can revisit and try to find out where is the nonlinearity and how is that nonlinearity being productively used in order to create a limit cycle. And in nature also, wherever there is a necessity of a cyclic motion that is needed to be stable, you have limit cycles. A very common example is the human heart. So, a human heart's pounding, the motion is a oscillatory motion obviously, and that oscillatory motion obviously needs to be stable. Okay, imagine that your heart goes by this principle, what will happen? Suppose your heart is something with a linear system, purely imaginary eigenvalues. So, it will have the same kind of cyclic motion. So, what will happen? What is the problem? Yeah. So, supposing there is a cracker bursting here, immediately it starts pounding faster, and for the rest of your life it goes on pounding faster. So, obviously that is not allowed. Go for a jogging, you have got a greater heartbeat, and for the rest of life you are locked with it. So, that is obviously undesirable, and that does not happen. So, your heart is a limit cycle. Similarly, everything that you see around yourself, where there is some kind of a cyclic motion, that is always a limit cycle. I am not talking about this motion of the moon around the earth or something like that. These are not the cases I am talking about. I am talking about the naturally occurring rhythms, where you have a rhythm which in the biological world or in the natural world you find there is a rhythm, there it is must be this. Okay, so, we have understood that in a nonlinear system there can be a limit cycle. Notice that the limit cycle is not a local behavior, because locally it is just outgoing orbit. By starting the local area, you would conclude that it would be unstable, but it is not unstable, it is a global behavior. So, it is a global behavior of the whole of the state space, and that is why it cannot be studied in any means if you only concentrate on the local neighborhoods. So, these are some typical features of limit cycles. Now, if you have a limit cycle like this, what is this and what is that? What are the axes? The two states, say x and y. Now, you could also plot the x against time and y against time. What will you get? If you plot, say, an orbit like this, and if you plot x against time, so you will get what? No, it is not a sinusoidal motion. That is what I wanted to point out. It is not a sinusoidal motion, but a periodic motion. So, something like this maybe, but it is not exactly a sinusoid. Why? In order for it to be exactly sinusoid, you need really this. If you have a purely imaginary eigenvalues, then we have seen that yields sinusoid. So, if you do not have, then depending on the character of the state space, it will be not exactly a circle, bent here, bent there, pressed here, squeezed there, whatever it is, it will be some kind of a orbit, but not really a circle or ellipse exactly. So, if it is not, then it will not be purely a sinusoid, but it is a periodic waveform. Now, let us ask, in what way can we have okay, what will be the y waveform? What will be the y waveform? Shifted in phase, but the waveform would look the same, right. So, it will be shifted in phase, but it will be more or less the same. Now, if I ask, is it possible to have something like this? Is it possible to have something like this? No, because what is this point? At this point, the orbit is intersecting itself, which means that if you exactly are here, then where is the vector? One thing says like this, another thing says like that. Obviously, it is not possible, because for every point the vector is unique. So, this is impossible to happen physically, right. So, such an orbit would normally not occur. But then wait, why did we say it will not occur? Because in order for an orbit like this to occur, there has to be an intersection, and intersections are prohibited. But then suppose it is not a 2D system, but a 3D system. In that case, what you are seeing as the intersection could actually be orbits that are separated along the z direction. So, in that case there will be no intersection that will be allowed. Is that clear? So, such an orbit will not be allowed in a 2-dimensional system, but such an orbit will be allowed in a 3-dimensional system. Like you have seen, a sinusoidal oscillation is not possible in a 1-dimensional linear system, but it is possible in a 2-dimensional linear system. Similarly, an orbit like this is not possible in a 2-dimensional nonlinear system, but is possible in a 3-dimensional and above nonlinear system. If you have an orbit like this, these are actually real, they happen. Now, if you have an orbit like this, then what would be the evolution of the x coordinate against time look like, and the y coordinate against time look like? Say, if I am plotting here the y coordinate against time, say I start from here, after that it goes down, after that it goes down, and after that it goes up. So, after that it goes up, then it goes down further, then it goes down further, then it goes up to the same value, right. Is that clear? So, actually you have to develop the ability of translating a state space behavior into a time domain behavior by arguing like that. So, at this point it goes, when it turns around, you should not think that in time also it turns round, because in time it cannot go back, it always goes forward in time. So, it goes down, down, up, up, and so on and so forth, and this orbit will repeat. Now, notice that in this one you have started from here, you have come here. So, starting from here, ending here is one cycle, peak to peak, again from here to the peak, again another cycle. So, there are 2 cycles, and after that only it comes to the same value, right. There are 2 periods, 1 period and 2 period. If you are thinking of the zero crossing, start from here, 1 period, 2 period, and then only it comes to the same value. So, it actually has 2 periods inside its complete cyclic behavior. That is why it is called a period 2 limit cycle. So, a period 2 behavior in general, if you want to see such a thing on the CRO screen, it would normally be something like this. Where the same behavior is repeating after 2 cycles, 2 periods. Now, the immediate conclusion about this is that such an waveform is not possible to see in a two dimensional system, right. That is what we have concluded from this. So, such a waveform you will never see in a two dimensional system, linear, nonlinear, whatever, it is not possible to see, theoretically impossible. So, if you have only two storage elements in a system, you know that in a when we talked about Born graphs, we learned that the number of storage elements would be equal to the number of state variables. So, if you have only two storage elements, you will never see something like this, clear. So, is the period 2 concept clear? That is what a period 2 is called. Now, if you can have an orbit like this, why not an orbit like this? That is also possible then, right. What is the difference between them? This one has 2 loops and this one has 3 loops. In this case, you can easily see, we have seen that the same state comes back after 2 periods, 2 cycles. In this case, the same state will come back after 3 cycles. So, this is period 3. So, this is period 2. What about that? Possible? Well, at least you will not be able to argue that mathematically that it is not possible. And there is a nice saying that if something you cannot prove as not possible, it must be occurring in nature. So, this will also occur, such rather complicated orbits are also possible in nature. So, this would be 1, 2, 3, 4, 5. So, these are perfectly possible. So, the point is that in a linear system none of that could happen, but the moment you shake off the possibility of that nice linearity character, all possible behaviors are then possible. Now, notice that here we had initially started with a periodic orbit, period 1 orbit, first established that such a thing is possible, then this is period 1. Then we said the period 2 is possible, then we said the period 3 is possible, and notice that all the time how are we computing this? Simply by starting from an initial condition and then going on by some kind of a numerical routine, and you have already learned the Runge-Kutta numerical routine. So, all these will have to be done that way, remember, it cannot be done by any of the linear means. So, starting from any initial condition you go on, and but if you start from another initial condition here, what will happen? Then if it is a limit cycle, then it will converge onto that, it will slowly progressively go closer and closer to that limit cycle, and finally it will converge onto that. In that sense, this is also a limit cycle. Okay. And we have said in the last class that these are sort of gravitating bodies in the state space, in the sense that if you start from another initial condition quite far off, it gets attracted to this. So, these are also called attractors. So, you would see in books reference to say period 1 attractor, period 2 attractor, period 3 attractor, period 5 attractor, which means that these are attracting in the state space. Clear?
So, but how can we we always share that if we start from a very distant point, then it will always get on to that orbit. It is quite likely that we will have another.
Yes, I will come to that. What he is saying is that supposing in the state space there is somewhere an attractor like this, does it always mean that all the state space will be attracted to this one? There is no reason to believe that, because we have the first point that we noted in a nonlinear system was that the state space could have different behavior in the different parts. So, there is no reason to believe that there is from somewhere it will also converge onto that. It could be converging onto another, say an equilibrium point here. So, from here it goes, but from here it goes, which means that there is one attractor which is attracting a part of the state space, there is another attractor which is attracting another part of the state space. It is possible in a nonlinear system. In that case, it is also possible that, not only possible, it must happen that there should be some kind of a dividing line, so that this side goes to this one and that side goes to this one, like your football fields, one hostel plays there, the other hostel plays there, in between there is a line. So, you cannot cross the line. So, you have, if you are in this side, you always go to this attractor, in this side this. So, then the region of the state space that is attracted to one attractor will be called the basin of attraction. So, there is one basin of attraction here, there is another basin of attraction here, and the dividing line would be called the basin boundary.
So, do we have an upper limit which defines the number of basins of attraction that we can have in an n-dimensional system?
No, his question is that how many such basins of attraction can there be? Is there an upper limit? No, there is no upper limit. There is no upper limit. In a nonlinear system, there could be very large number of such attractors which are existing at the same time, often called coexisting attractors. So, you have different attractors in different parts of the state space, and there is no upper limit, but one thing is sure, that the number of attractors are also related to the number of equilibrium points. For example, here there was an equilibrium point inside which had become stable, and so this fellow is now the attractor. Here is, I can see that if it is a point, then it is a point attractor, which means it is also an equilibrium point. So, similarly, I am not going into the mathematical details of it, but at least it does sound intuitively possible that the number of attractors would be related to the number of equilibrium points. Okay. That is why it cannot really be infinity. No, it can be infinity. For example, the pendulum itself has infinite number of this. It could be, but it is definitely related to the number of equilibrium points. That is all. Such details I will come to a little later. But then, if you can have orbits like this, period 1, period 2, period 3, period 5, why not period 16, period 28, period 73, period 135? Is there anything to stop it? No, at least not mathematically. So, if you extrapolate that argument, then you evidently reach the conclusion that there is no limit to the periodicity of an orbit. It could be a million, it could be infinity, right. Now, what is the meaning of a period infinity? It just means that it is an orbit that has no periodicity, it does not come back to itself, that is all. Yes, it is possible. It is possible to have an orbit that never comes back to itself, so that as it goes around, it always traverses a new path, and still it is bounded. That means you can have an oscillation like that. Let us understand that slowly by working with one example system. Let us take this system. It is called the Lorentz system. X dot is equal to minus sigma x minus y. This is a linear equation. Y dot is equal to minus x z, this is the nonlinear term, plus some r x minus y, and z dot is equal to x y, this is another nonlinear term, minus b z. So, in this system there are a few parameters I can see, x, y, z, z are the variables. Parameters are I can see sigma is a parameter, I can see b is a parameter, I can see r is a parameter, right. In such a system, obviously we will not be able to do the simulation by simply working analytically, but let us try as far as possible, as far as we can do. For that we need to assume some parameter value. So, let us say sigma is say 10, b say 8 by 3, and r okay, we will be able to arrive at some conclusions depending on that. Firstly, what are the equilibrium points of this? No, 0 0 0 is 1. If you set the left hand side to 0 and 0 0 0, yes, so it is an equilibrium point. So, equilibrium point would be 0 0 0. Anything else? There should be, because these terms are there. So, can you just work out what are the other equilibrium points? 0 0 0 is definitely one equilibrium point. Okay. The other thing is, what is the Jacobian matrix of this? Minus sigma, this is plus. So, sigma 0, this is minus z plus r, the second term is times by minus 1, third term is minus x, okay. Then this is y, x and minus b, right. So, this is the Jacobian matrix. If you put 0 0 0, you get this is 0, so r remains, fine. You substitute this and find out when will this equilibrium point be stable. Firstly, what are the other equilibrium points? The other equilibrium, there are 3 equilibrium points. A is 0 0 0. The other equilibrium points are, you have noticed that it is rather simple to work out, but in order to save your time, let me write them: root over b into r minus 1, root over b r minus 1 and r minus 1, and c is mirror image of it, minus root over b r minus 1 minus root over b r minus 1 and r minus 1. Now, this immediately tells that so long as r is less than 1, this term will become imaginary, and it is a real state space in which we are talking about the location of an equilibrium point, and that cannot be complex, that cannot be imaginary. So, whenever it yields imaginary numbers, it will only mean that the equilibrium point does not exist. So, this means that for r less than 1, b and c do not exist. Okay. And when that is so, then what is the status of this point A 0 0 0 is stable. Just put this and put these values, you will find that when these fellows do not exist, A fellow is stable. So, what happens is that there is one equilibrium point and all the initial conditions will converge onto that, fine. But as you move the parameter r through 1, as it becomes greater than 1, these two equilibrium points start to exist. Before that it was not there. So, notice another typical feature of a nonlinear system, that as you change a parameter, new equilibrium points may start to exist which were not existing earlier. Again a situation that you never come across in a linear system. So, the number of equilibrium points are not really fixed, they also depend on the parameter values, and how to decide when they exist or not exist, that is by whether or not you are getting real numbers when you actually try to solve this. If you get real numbers, they are existing. If you do not get real numbers, they are not existing. Fine. Next step is to inquire whether they will be stable. How to inquire that? By looking at the Jacobian matrix and its eigenvalues. So, just substitute this, we have everything, right. The position of the equilibrium point is there, the values are there. Position of these equilibrium points are there, values are there, just substitute. You would find that for r less than say 24.74, B and C are stable. You would have do that exercise later, but you have understood how to do that exercise, that you will simply put it here, find the position B and C, and then you put the values here, obtain the eigenvalues. In place of this x and z and y, you will put these numbers, so that you can exactly obtain this matrix and its eigenvalues. Trivial to do by MATLAB. So, just in 5 minutes you can do that, and then you will see that for this condition, these eigenvalues, the eigenvalues of B and C would be would have real part negative, and then at that point it becomes real part exactly 0, and beyond that it becomes real part positive. Okay. So, what do you expect the behavior to be then? The behavior is below r is equal to 1, only one fixed point is existing, the others are not there. When r becomes greater than 1, this fixed point becomes unstable, and there are two fixed points now that have been born and they are now stable, but they have complex conjugate eigenvalues. So, it will spiral around, okay. 3D state space, right. In a 3D state space, we have already understood the local linear behavior around the equilibrium point, what the behavior will be, that it is 3D. So, locally it will be a 3D linear system harboring at least a pair of complex conjugate eigenvalues, the other eigenvalue must be stable, must be real, okay. The other eigenvalue must be real. So, in this case the other eigenvalue will have a corresponding eigenvector along which it will converge onto that, and it will converge onto the eigenplane associated with the complex conjugate eigenvalues. How to obtain that? See, this is where whatever we learned in terms of linear system would be actually applicable, in the sense that you start from here, there will be a plane, it will converge onto that plane first, and then it will do whatever it can do depending on the eigenvalues, whether the real part is negative or positive. If it is negative, then it will converge along that plane. If it is positive, then it will diverge along that plane, but along that plane, where is that plane? So, we have learned that for that we have to divide the corresponding solutions into the real part and the imaginary part, and the imaginary part itself is a real number times j. So, the real part will give one vector, the imaginary part will give another vector, and the plane passing through these two will give the plane corresponding to the complex conjugate eigenvalues, right. all these are somewhat difficult to visualize, right. So, let us try to visualize that. If you really solve it, what happens? Let us try to visualize with a example. Well, so this is the equation for the Lorentz system that has been put in, and R I have set as 15, the rest of the things are as they are. So, start from here, see the evaluation. It first approached it rather fast. Why? Because its corresponding eigenvalue was very small, or negative large number, sorry, not small, a negative large number. So, it approached very fast, and then it was converging onto that equilibrium point. I can see it is here along a plane. Can you see the plane now? It always does so along a plane. But this is one of the equilibrium points. There must be another equilibrium point also. Okay. So, let us change the initial condition to, I will put a minus sign here, so that I can start from some part which is here. This is x equal to 0. So, this is x positive, I want to start from x negative somewhere here. So, I will just put a minus sign, and then I will see its behavior. No, it goes to the same one. Okay. Then let me change it further. Maybe I will put minus here also. Yeah. See, a different initial condition, it goes to a different orbit. Okay. Can you see its plane? So, there are two equilibrium points. The two equilibrium points, both of them have the same, they are actually mirror image of each other, and if you substitute them, you get the eigenvalue is also a mirror image of each other. So, you have more or less the same convergence property of the two. Now, probably you would like to see them, say them together, right. So, let me do it for orbit 1 and orbit 2. 15, 10, 40, okay. I will give the numbers, 15, 10, 40. Happy? Starting from two initial conditions, it is going around and converging onto two different equilibrium points. That is one of the properties of a linear system. Now, tell me what will happen if I now progressively increase the R. If I progressively increase the R, what will happen is that if you see the, then you will see that so long as R is less than this, they are stable, which means the real part is negative, and then it goes through real part 0 into the positive side at this value. So, if I now go closer, for example, 22, what do you expect? Physically, what do you expect? The real part will be small, which means the decay rate will be small, which means that it will convert onto the equilibrium point, all right, but it will be very slow in doing so. Let us do that. That is what our theory would say. Let me say put 22 here and very slow, right, but still you can see there is a e to the power lambda t kind of term. Can you see the e to the power lambda t? Yes, you have to see, you have to be able to see the e to the power lambda t term. Now, if I increase it through the 24.74, maybe say I make it 26, then what will happen? Then see what happens. they are going out, right, but then after some time they now what has happened? There are two planes corresponding to two different equilibrium points. Those two planes are not the same plane, so there should be intersection somewhere. Okay. And moreover, along one the rotation is clockwise, along the other the rotation is counterclockwise. See. Okay. So what happens is, after some time this fellow gets thrown into this one and then it rotates clockwise. Here it is counterclockwise and here it is clockwise, and then after some time it gets thrown into the other one, so it cannot escape, it gets locked, but then both are unstable and so it goes on in that. So this is one way in which an orbit can be created, where you see it does not repeat the same state. If it repeated, then you would see in the same place it is going on and on and on. It is not that. And if I do it for a larger time, say I will make it 100 seconds, and I will make it larger. Yeah. Now if I forgot to stop it. Yeah. So this is an orbit in which nothing is really being repeated. Can you see? They are always going through a different route, different path. None of these paths are actually intersecting, because it is actually 3D system. And it is possible to rotate it, then you see the positions. For example, if I rotate it, I will make it faster. Now if I see from different angles, you can see the whole thing happening. I will make it faster. Now if I change the positions, from different angles you can see this, and you can see the planes, right, two different planes. Normally it is convenient to see from this angle, yeah, but you can also see from other angles where it looks quite different from different angles, but all the time you are seeing actual projections. Fine. So you can see that there is one cycle like this, there is another cycle like that, and from here it gets thrown into the other cycle here, and from here it gets thrown into this cycle here, and they are not really intersecting lines, they are separate, and that is what can create an orbit which is also an attractor, in the sense that if you start from an initial condition somewhere here, it will converge onto that attractor. In that sense, it is also an attractor, and it is still a completely aperiodic behavior. There is no periodicity in it. If you see in time domain, it will be completely aperiodic behavior. Now that is what is known as chaos. So chaos is nothing but a bounded aperiodic behavior in a dynamical system. Okay. So such behavior can also be in a nonlinear dynamical system. So this is called chaos. Let me write down the definition. So, it is pretty simple really. All that is happening is that we have found that there can be period 1 attractor, there can be period 2 attractor, there can be period 3 attractor, there can be period n attractor, and why not then take n to the extreme limit, which is infinity. In that case, it is completely aperiodic behavior, and that is exactly what we are talking about. So, that is what is chaos. There are other things which I will come to a little later, but there is another important issue here. The issue is that suppose you start from this initial condition, which I have given, probably it is too small for you to read. So, let me write down the initial condition that I have given. X is minus 15, y is minus 10, and z is 40. Now, if I start from a very close initial condition, another initial condition, say x is equal to minus 15.001 and y is equal to minus 10 and z is equal to 40. We can start from those initial conditions. So, this is orbit 1 minus 15 minus 10, no? Okay, I will put minus 15.001, a very tiny difference, minus 10, 40. Okay, now, if I start, I will make it slow. You can see one line. Why? Both are being calculated, but both are absolutely going together. That is why you do not see them. They are actually 2 points. That is what you normally would expect, that it would be more or less the same way. But now they have started to separate out. Can you see that? Okay, now see they have gone in completely different directions, right? Which means that if you start from different initial conditions, however minute that difference be, they all evolve in different directions. They will never follow each other. That is one important property of a nonlinear of a chaotic system, which is known as sensitive dependence on initial condition. Sensitive dependence on initial condition. So, if you make that, if you might argue that okay, make it 0.00001. So, what? I have made it the difference after at the 5th decimal place. So, if I now stop it and I will make it faster to avoid wasting time. It is still going together, still going together. Still going together, starting to separate out. Now, they have gone in different directions. Can you see that? So, that will always happen. The character is of the system is such that two ultimately arbitrarily nearby initial conditions will always evolve in different directions. What the technical implications of that is, I will come to that in the next class. Okay? Fine. Thank you for today.